Thank you, and thanks for staying so late. So you guys must be the hardcore people interested in finding bugs in software engineering and machine learning. Uh, so some background about my motivation to do this. Over the last 20 years or so, I've played roles in very different aspects of software engineering, both as a developer, as a manager, as an architect, both at the software level and at the database level. And I've been very frustrated by the lack of structure in the underlying processes of software engineering. And the way I think about it today is that we are in an industry that's an advanced stage of craftsmanship with power tools. And we are about to make a transition to industrial production of software, but we don't have the means, we don't have the measurements, we don't have the instrumentation needed to do these things in an automated fashion, and so we end up doing them manually. So that's, you'll see some of that later, but my motivation is to take the emotion and the cherry picking and the craziness out of reasoning about software and actually making it reasoning about software. So the rest you'll see as we go along. So about me, I have a bachelor's in EE from many years ago, before the meteors came and the dinosaurs died. I went and did a master's in applied math, and then I was in a PhD pure math program, and it got too crazy, so I did everything but thesis, and I went back to software development. So as I've mentioned, I've done all of these things. You're free to look up Learn Data Science. HTTP learnds.com is a bunch of IPython notebooks to teach yourself data science if you're a software developer and want to go in and learn that. It comes with, you just clone the Git repository and you get everything, including the data sets and everything. So I encourage you to do that. And so I was in a recent project with a company called Perforce, and some of the older people may have used Perforce. Some of the newer people may have been forced to use Perforce. But I learned a lot about version control systems, and there are some very positive things about Perforce that are often missed, and one of them is that it saves all the history of your project, which means that you can do data mining on it. And so one of the things that came out of doing that project was that I bootstrapped this startup and started doing data mining on software repositories, not just Perforce. So what we'll do is we'll look at the current state of software development and see what is the meaning of risk in software development and how do we quantify it, because there's always risk of things breaking, of not delivering software, of many different things. And we often argue about it intensely, but we don't have a base to reason from, a data-driven base to reason from. Increasingly, with applying analytics to some parts of it, we're getting better. But what I'll show you here is that there are major aspects that are missing and some things we're doing just wrong, and hopefully we can do this better. So the idea is, how do we make this more industrial-like? And to do that, we need to have some instrumentation and sensors and to create feedback loops so that it's not an open-loop control system. Most of the times you run it and then it breaks, and then we say, oh, man, that broke, and then we start over again. And so we can try to surface errors early. That's what feedback loops do. They're very early measurements of errors so that corrective feedback can be applied. And are there signals in the software engineering process to do that? So notice I'm not saying that I'm going to get into your code. So that's the first thing to notice, is that I'm not analyzing code. I'm not understanding the language. I'm looking at the various artifacts that come out of the software engineering process, which is commits, issues, and in the future logs, and even after that, the story text. So I want to look at all the metadata of the software engineering process and to see if we can see signals, and we can build correlative and predictive models based on this, which makes it then language independent and makes it independent of the particular tools and techniques you might be using, because all of this is also information about your software engineering process. And the idea is, can we use it to predict things? And so how do we do this? And the why can't we have nice things is because the software always seems easy when you start, and then when you're close to delivery, it seems impossibly hard. And this has not gone away. And so until we fix this, until we have an idea of how do we predict how our project is doing well ahead of time and identify these areas in a reasonable way, in a way that we can quantify and reason about, then we're doomed. And so the idea that I mentioned earlier is that we're at a cusp from craftsmanship with power tools to industrial production. And yet our tools are still sort of Stone Age tools with polish. And we have a sort of way of speaking about these things, internalizing some of the lessons and passing them on, which is not scalable. And that's why we have a theory that if we have enough wizards, then we won't have any problems, but wizards don't scale. And so that's a zero-sum game of trying to hire away wizards from other people. And what we really need to do is to take the knowledge about the process that we've learned and make it available to machines which can scale easily. And then the humans can do the creative part. So that's the big picture, is how much of this knowledge can be used by machines to scale up our processes better. And so if you've seen The Martian, then the last line will make some sense to you. But basically, we are trying to apply science to the software engineering process. And in other industries where they have very complex processes that go on, very, very dangerous things. I mean, this guy standing next to this boiler, if everything was not controlled, it would explode and kill him. But we have confidence in our systems because over the years, we've taken our knowledge and we've externalized it, we've taught it to other people, and then we've put it in these sensors and instruments that have encoded all this collective knowledge over the years, so that a little reading on a valve can tell us, we need to release pressure from somewhere else. We don't have these sensors in software engineering. We don't know where to release the valve to release the pressure that's going to cause this project to blow up 2 months down the line. And so that's what we want to be able to do if we can do it. And therefore, since we don't have that, we can't have this big vision of what is my software in my enterprise doing. In Fortune 500 companies, often they have software, they have hundreds of applications, but they don't know who's using what and which application is obsolete, and can I shut this down and not use it anymore without somebody in some remote department saying, hey, I can't do my job anymore. So we need a way to effectively build what is the SAP of software applications and assets so that we can manage them better. But we are way far from that. What we need is feedback loops. In a typical industrial system, you have these things that identify errors and then apply corrective loops, and we don't have those. And what we have instead is a bunch of acronyms and a manager that's worried about what is this new acronym that's come along, and will it help me ship faster, better, cheaper? But developers want to have this latest acronym on their resume, so that's what we use, and then it blows up, and then we curse. So this is in my sort of, I drew this, by the way, this is my picture of software development as it is today. Thank you. But let's take a look at it from an industrial production point of view. These are the various stages we go through in software development. And we throw away most of the things that have the signal. That's the thing that I've identified as data exhaust. And it's data that comes as a side effect of our software engineering, and it contains a lot of signals. We can correlate some of these signals. For instance, run logs might tell you what files contain a particular bug. And we might want to save them and look at some correlations between changes we made and how things crashed in the field, or even when you're running tests, but we don't. And so we lose a lot of this information, but that's the stuff that I'm pulling out, and I've started with issues and commits and issues for some specific projects, and I've done this over 3 or 4 proprietary projects. Perforce was my first customer, and then over a bunch of Apache projects. And what I found is that there is a wide variation in the discipline on how we do software development, which makes it either easy or hard to build these correlative models, and I'll talk about that in a second. But the stuff that you see on the right, the featureized model predict, that's what we do at Numeric. And then we want to take these signals and put them back. So you can see that this is the beginnings of a feedback loop. And so 2 things that we've done, one of which I'll show you, is to actually extract features from commits that from your own history make them buggy. And so the next commit that comes along, I should be able to tell you, hey, does this look like a buggy commit or does this look like a clean commit? And I should be able to give you a warning with the understanding that it's not always 100% correct, but I should be able to warn you of the commits that come along. And then you go and you hopefully get it reviewed, or you go take a second look at it. And so that's how we started, and we built basically a random forest model over a lot of the attributes that we extracted from commits and issues. So that's where the scikit-learn and random forest came along. And what we found was there was a risk score or a number that was being applied to each of the files in the system. And so I tried to make sense of this as why are certain commits considered buggy, and why are certain other commits being flagged as safe? And is it have to do with the files that are in this? Does it have to do with the developer? Does it have to do with the time it is checked in? So all of these things matter. But the question I was not able to answer is it because of the file? And that was really problematic, because I wanted to know if there are certain files that are buggier than other files. And what I wanted to do was to go backwards from files to bugs. In other words, tell me all the bugs that have been logged that include this file. And what I found was you can't do that with our systems today. So hold that thought for a second, and we'll go ahead. So the questions we want to ask is, can we build a predictive model, and can we use it to get early warnings? And can we use it to do what-if analysis? Like, what if I added more people? What if I wanted to get more done? What if I release today, et cetera? And can some recommended best practices come out of this that help me improve this stuff? And can it show me stuff that I don't know? So surprising results is always a useful thing when you're building a predictive model, because if it predicts stuff you already know, then it's a complete waste of time. So the short answer to all of that is yes, and we'll see how we can do all this. So again, a little cartoon version of software development. And what we have on the left is what typically happens, and you shouldn't get too much importance to the shapes of these things, except that you always want to keep adding features, because to stay competitive, your software has to evolve, and there are market pressures to keep adding features. But underlying this, complexity grows, and you have to keep dealing with increasing risk, except you don't know what that risk is, and you can't put your finger on it. And so management of complicated software projects is done by gut feel, by people who've done this before, people who have internalized these lessons but can't tell you why they think things are going better or worse. And what my goal is to extract this information and externalize it so that you can make decisions. And you can see on the right side, you have the risk line has become solid instead of the dotted line, which suggests something going on that you can't put your finger on. And the green line is some sort of safe thing that we have. Each person has a different level gut feeling of what is safe and what is not. And what we really want to do is to externalize this risk and to damp it, because we now can measure it under whatever it is that your local measure of safety is. And so here are questions that we can barely answer today. What are my top 10 buggiest files? I couldn't answer that question. So why would you want to know that? Because maybe you want to focus your testing on that first before you build tests for all the other stuff. And there's some very interesting thing that comes out of this, that we're really doing testing wrong. And now I want to intersect this. What are my top 10 files that are buggiest and change the most? Because if I tell you that these 5 files have historically the most bugs, and oh, by the way, most people are working on it, so your hair should rise at the back of your neck, thinking this is where most future bugs are going to come in. So can we correlate changes to bugs? And the real question is, what do we need to do that? And the funny thing today is that we can't correlate changes to bugs with the tools that we have. So why is that? And this is one picture about why we can't have good things. So these solid blue lines here suggest that there are some barriers in between these data stores. And so we have changes in one area. And if you use Git and Jira, then the first two apply to you. And if you use Perforce, if you're using their job system, which is an ability to actually put tasks and your commits in the same data store, then you don't need any of these others. But what you're seeing here is that in your software development pipeline, you have various artifacts that are coming out. And the problem we have is that we can't correlate them in the data formats that we have today. So one of the first things I started by doing was to get issues and to get commits, and to find which commits ended up, which commits were bug fix commits, which means that was the area where the bug was. So I look at bug fix commits, and then I look at Jira issues, and I try to correlate them. And this is where the difficulty lies, because in many cases, people are not following a disciplined approach of putting the bug fix, the bug ID in the commit. That simple act of putting the bug ID in the commit bootstrapped this process of industrial modeling of this process. And if we don't do that, then the causal connection is lost, right? And because we don't know what change is fixing what bug, and we want to be able to do that. And if we can't, then we better be doing that. And this is the underlying, what I found is an underlying, are people familiar with entity relationships diagram, or is it a thing that is dead now? But what we have, F stands for files, I stands for issues, and C stands for changes. And this is the underlying model, almost a canonical core model of software development. And this is what I discovered when trying to find the reverse connection between issues and files. And that dotted line there is that I can't find that unless I do something with the data stores that I have. And so as you can see, each of these different things, Git, Jira, Pivotal Tracker, they're like the blind man and the elephant. And they're looking at different attributes of the same bigger entity, and they are not getting the big picture. So if you go back here, what my company Numeric has done, and we'll be open sourcing various aspects of this in the future, is to extract all of this stuff into a common data model. People who do BI and data warehouses and fact tables. Is a fact table, anybody mean anything to anybody here? No one. Fact table, okay. So what we've essentially done is create a data warehouse and build fact tables for all your software engineering history. And then the measures are actually the severity. We've created a synthetic measure of severity, which is how much residual unfixed bugs, if that's a way to think about it, remain in this area. So once you do that, then you can do traditional BI and build cubes, and you can do all kinds of interesting stuff there. That's when we can have good things. And then dashboards that everybody loves. And if you're not the dashboard type, then you can actually give you a command prompt where you can sit down and do queries on it. And so the what if part comes out of this. So what is net severity measure? So it's something that's lingering risk or ways to think about it, although it's just a number. How is the risk distributed across files is a way to think about it. The file level. And then once you can go down to the file level, you can aggregate it up to modules and other higher things. But most importantly, it's to think of a measure of, aside from risk, it's a measure of technical debt, because there's stuff that needs to be still dealt with. And maybe the answer is not to fix it, the bug, but maybe it is to refactor. So whatever it is, it's a measure of work that remains to be done. And so that's kind of the core software development lifecycle dimensional model for people who are familiar with these terms. So current metrics. What we get in the current world is something called a burn down chart, which tells you how we are fixing bugs and how many bugs remain to be fixed before release. And so that's got time on the x-axis and number of bugs on the y-axis. And then you have this commits versus time. It's like how features are increasing and how much activity there is, which is number of commits versus time. But so in all of these cases, time is the independent variable, but in reality, time is not the driver of breakage. It's changes that are the driver of breakage. So unless you join these two together and make commits as the independent variable, you're not going to figure out how brittle your code is. Because what you really want to identify is what areas of your code can be changed with less breakage, and what area of your code can be really have to watch out for. And on some level, for a small enough project, everybody knows where the skeletons are buried. And everybody knows not to touch that one file or that area. Don't touch that area. Only XYZ knows, and now he's left the company. This is not an uncommon occurrence. And so there are areas of the code that using stuff like this, you can surface them, you can quantify them, and you can go to the powers that be and say, look, the amount of stuff that we have that needs to be fixed, and so that needs to be in your next budget, or that's what we need to do for a while. So the idea here is that using this kind of quantification, you can have a reason-based discussion rather than this gut feeling discussion that we tend to have. And I've been on all sides of this. In this, I've been the person at the other end saying, "Give me proof," and I've been the other side saying, and cherry picking some things here and there and trying to prove your point, for which there are counter examples. And so, what I'm trying to do here is to build a scientific model of how risk is distributed over your project. And so, brittleness is a word to keep in mind. And so, we built this thing called the numeric quad risk model, which basically says where the changes are low and the changes are high, and where the breakage is low and the breakage is high. And this, by the way, we can see from the previous model. When you built this BI model, you can do sums and counts on different dimensions, and you can find out which files have high changes, low risk, et cetera. And so what you want is that the stuff that's red above that line is the stuff with high breakage. Now, I'll explain these letters. BR stands for brittle, U stands for unstable, D stands for done, and S stands for stable. And I'll explain that in a second, with the caveat that the U is where all files begin their life in this unstable mode, where you're writing and changing and writing and breaking and changing. But eventually, they migrate to these other areas. And what you really want is that the stuff above the line should not be growing as your project goes along. So if you remember the cartoon that I drew, there was this green line, dotted line. You can think of this line as that dotted line. And if stuff starts moving up above this line, then your project is moving into a riskier phase for whatever reason. And if that's happening towards release, then that's a problem. It can happen for a period of time when everybody is working on the new features, and then the testing begins, it has to go down, it can't get unstable. And that's a very simple way of thinking about it. So one of the things that I put some numbers in there, one of the things which I'll talk about in the meantime I found out on many of these is that a typical code base, 3 to 5% of the files have most of the severe bugs. And 80% of the files don't have any severe bugs at all. Some of them don't have any bugs at all logged against them. That doesn't mean that there is not a bug there, but I'm looking purely at history, bugs that have been logged in the past. And when you do that, so I've put in some numbers here. 3% are brittle, and assume that 10% of your code base is changing for every iteration, and that's 13, and I just made up some other numbers to put in the bottom. The idea here is, these are percentages. So even if you keep adding files, this is a percentage number. So from 1 week to the next, from one iteration to the next, are the numbers above the line growing higher, or are the numbers below the line growing higher? And if above the line the numbers are going higher, you have a problem. And below the line, if your numbers are going, then you're going better, and you're able to damp the risk. And you can go back and drill down, and I'll show you how we've actually visualized this for a couple of projects. The HBase project is a project that I started off with, and now I'm right now doing it for the Apache Spark project. That'll be another couple of days. And some of this will be open sourced, and I'd like people who are interested in this to please join me. I've been doing this alone with a team in Ukraine. And I want to open source this stuff so that people can take some of this stuff and start improving the software engineering process, but also contribute your results back so it can be a learning experience for the industry. And this is very early, but I think there's a lot that can be done here and a tremendous amount of value that can be created for everybody. So this thing that you see on the screen can even be on your phone. And your project manager can be just looking at these numbers every iteration, remotely, every day if they want, if that's when you update the stuff. And this is the kind of conversation that we have not been able to have between engineers, their managers, and all the way up the chain forever. And so going back to this, what I'm saying here is that this diagram is sort of a quantitative version of this thing, where if you can keep your files below that line growing, then you've damped the risk. And this is a little bit hand-wavy, but I hope you've seen the quantification behind that. Now, this is the thing that I wanted to show you is, and by the way, power laws happen everywhere in software engineering. If you go look at the research, there are a lot of people at universities that do research on software engineering and quantitative research, and they find not just bugs with files, but a lot of other issues have power laws. And so it's not normally distributed, and it's not uniformly distributed. And so the problem we have in the industry today is that test coverage assumes that risk is uniformly distributed across your files. And if you look at this diagram up there, take a look at the area in the left. There's a tremendous amount of risk, but we don't have coverage of that. And then stuff to the right is where we are wasting effort. And so one of the things that came out, the surprising thing for me that came out was that maybe if you start by focusing using these numeric measures, the area where the biggest risk lies, your effective coverage of actual risk would be better than simply looking at lines of code and files. And it would be more effective, the same amount of resources would be more effective in actually catching bugs as opposed to consuming CPU cycles every time the continuous integration kicks in. Because we're not only wasting 80% of the effort in a very hand-wavy fashion, but we are also doing it now continuously every day. So we are more efficiently in an automated fashion wasting resources. So I'm going to take a minute and demo for you a visualization of how this would actually work in practice. And so I've taken data from an Apache HBase project and the Jira issues and the commits from Git, pulled them in, processed them, done all this joining and messy cleanup stuff, and built effectively a cube. Give me a second. So this is now, if you're familiar with Tableau, this is something we've created in Tableau. And I'm going to explain a little bit of what all this stuff is. So first, let me remove this part. So what you're getting here is simply the areas, the times of the year where what green stuff means and what red stuff means is this. We compute something called brittleness, which is the severity, the net severity, which is an aggregate of high severity bugs. It's a measure of bad things. And in the denominator, we have change, how many changes we had. So there were 100 commits, and the net severity was 0.1. Or we had 20 commits, and the net severity was 20. So you will see red in the second one, and you'll see green in the first one, because a lot of change didn't cause too much severity to go up. And so this is actually measuring how the severity changed from one month to the next. Okay? So things got worse, and then they got better. And this pattern is something that you see in a healthy project. This is actually healthy, where you're adding features, and then you're logging bugs, and then you're fixing bugs. And this is a sort of a cycle that it's kind of a healthy heartbeat in a project that should be the way it is. What you don't want is you're about to release, and then you have a bunch of unresolved red things. And so I'm going to break this down now, and with the kind of data model we have, we can do that. So Apache projects have this thing called components. And every time you log a bug, you actually include what component it was. And often in Jira, yes?
Can you go back to the previous? I just wanted to make sure.
Previous slide or previous view?
Remove the previous
Yes, okay.
So yeah, that temporal pattern that you mentioned.
Yes.
I would imagine that there's some averaging going, because yes, these are bugs that they tested.
Correct.
And so therefore the red became green.
Yes.
But then the software then goes out into production, and
Yes.
real customers use it,
Yes.
and the bugs
Yes.
start to trickle in.
Yes.
So that's not really being accounted for.
No, I mean, that is not being associated with this time frame. It's being associated with when it's reported and then it gets fixed. So there's a certain lag. There's a certain lag in there that is in the nature of software development. We can peel these off, but this is kind of the very first attempt at this. So yes, it's more nuanced than what it appears. So let's go back to, what will we be doing? Components. So what you can look at now is, and I can remove this and remove this. So that's a better, and now what you can look at is a particular component, and there's a lot of activity going on. If there's a lot of whites, it means there's not a lot of activity going on. And you can see there's a lot of activity going on and doesn't break too much, but whoa, I hope that was not released because that was close. And so we can keep discussing these things. So areas where you have a lot of dark reds are, I would say, areas where some of the risk is located. And this is just one view. We can do some clustering on this because now we have numeric measures. We can do clustering on the numeric measures. We can do all kinds of things, and which I haven't done yet. And so this is how, for instance, it would look sliced by just the one level above files. Now, if you want to, the next thing we can do is go to priority. So what you can now look at is that in any particular thing, what were the critical bugs and how much of this is associated with that, and how fast are we fixing critical bugs? You want intense reds to be followed by intense greens, and you don't want intense reds hanging around for too long, most certainly not. And then what you can also do is, and this is the part where things get a little, how much? I have 5%. Hopefully I'll finish before that. So now we're looking at who's fixing the bugs, and maybe people need help with some things. Maybe people are overloaded. And one of the things that I want to really very strongly warn about is to not use any of these analytic tools as blunt weapons to fire people, right? Because some of this stuff shows how activity is happening. And typically, if somebody's having difficulty, my approach is, now this is a data-driven reason to give them mentoring and support. You've already taken all the effort to hire them and gone through all that overhead. Here's data to help them get better, right? So that's a person-based thing, sliced by module and time. And you can take this down all the way to the file level if you want. But for any one model, there are way too many files on this, and the information is sparse when looked at. So for a human being, it's more useful to look at the aggregated areas. So that's why I said where buggy parts of your code base rather than bugs in your file. And so those are the areas where, which I'm not correlating yet, is does it have tests? How many tests does it have? And is the coverage there? So this is an example of what you can do in a very early phase if you put your data in the right fashion. And so the takeaways, I would say, are we can't have good things because some of the things we're just doing them wrong. And our software engineering data is in silos. And there is a canonical data model underneath, but we are not using it. So what should we do? And there's gold in your repositories, but we can't mine it right now. So the one thing, if I would say, to take away from this, and you don't do anything, you forget my name, you forget everything else, but just remember this one thing is to put the issue ID in the bug fix commit. And preferably put it in a standard place everywhere. And an example of this, and if I have time in the Q&A, I'll show you examples of how this Apache Spark project does it. And they do it very well. And that's probably the best practice to follow, is that they put the bug fix in the commit message in square brackets, the Jira ID, followed in square brackets by the component that they're fixing it. So they have a lot of metadata in a strongly typed fashion so that machines can go and extract this information. When you don't have that, you can't automate this process of pulling this stuff out. So aside from actually doing this, I learned a lot about the state of software engineering discipline in the industry. It's getting better, and I think Apache is playing a big role just by following common processes. But include the story ID if you have some kind of an ID for your stories. And code metrics are important, but your code could be perfect, and your configuration could be wrong, and your stuff won't deploy. So the whole process, end-to-end, is important. And maintaining history is important if you want to get the best out of this, and maintaining structure in your process. So that's the sum of it. And if you want to learn data science, there's a learnds.com, bunch of IPython notebooks. You can follow me on Twitter for some machine learning, some comedy, and some other things. So anyway, that was my talk. On time? Yeah. So 5 minutes question answers, or?
We're early.
We're early. So we have 10 minutes of Q&A, and I can get into a little bit of code to look at if you want. But yes?
So I'm curious, what I missed it, one is that when you're putting down the information, collecting, do you actually put down severity of the bug?
Yes. So what I'm pulling, so the question, when you're collecting this information, are you collecting severity of the bug? So yes, what I'm doing is counting the top 2 severity levels as bug in my model. And I'm ignoring all the other levels, which are usually feature changes and requests and nice to haves and all of that. And I'm calling them non-bugs. Okay, so that's how I'm doing that. And that's the threshold, and then I'm doing some thresholding on that after I build my model.
Yeah, as you mentioned here, behavior change
Yeah.
is one of the biggest stumbling blocks.
Yes.
One is make sure you put a Jira ID for the bugs. If it's a bug-related commit, or if it's a feature-related commit, then put the PID or something like that.
Yes.
I would imagine you said, oh, in the future we look at sprint stories and all of that as well.
Yes.
Because timeliness is the other thing, and that's where again there's a behavioral problem where engineers have tasks in the stories, but then they don't mark them as complete, right? So like that way you don't have any clue as to whether.
Right. So I'm going to repeat your question. In the process, it's also important to mark things as done so that it's open versus closed. And that's important because one of the severity measures is how many open bugs do we have against this. And so, yes, I mean, that is more basic than putting the ID, is marking it as closed. But I understand. There are a number of these things. And my hope in the future is number of these things can be part of our tools. So when you open a commit, you can even click on the issue and say fix, and then it pulls up your IDE and populates this information. There's really no need for humans to be doing all this, right? So that's the longer term, is like once we built this metadata, and once we've done all this, we can use it to link up our tools and create a much more automated process. So the number of windows we have open and the number of cut and paste we do between entirely different kinds of data stores is ridiculous. And we ought to be doing all of that through a uniform interface. Anyway, questions? Yes?
Yeah, so you mentioned you take into account commits and consequently bugs that have been fixed.
Yes.
Is there some way you can take into account open bugs?
Yes, I do take into account open bugs, and the net severity is basically closed versus open. So it's open bugs is a measure of net severity.
How would you associate a particular file with an open bug?
Well, we are not able to associate things with open, but we can associate things that have been reopened. So that's a measure, right? Because if the bug was fixed and reopened, we get a lot of that. Some of the more severe bugs are opened and closed more times. But that's right now a gray area. What does get marked is against what subsystem are we saying? So somebody says it's a UI bug, or somebody says it's a database bug. So we at least know, not necessarily at the file level, but at the module level, that something happened. But it depends on the person logging the bug. Yeah. Anyway, if you want to talk to me afterwards about how I can apply this to your process, please call me or talk to me or pull me out. Yeah.
You're going to publish that Tableau thing for HBase on the web?
Yes. Tableau themselves have a Tableau public, and so one of the things. What I'm hoping to do is to make it interactive, because that's where the power is. But then you have to put the whole model somewhere and host it.
Yeah, but having some kind of dashboard like this for every Apache project would be.
Yes, that we can do. Yeah. Okay, thank you.